Okay. I wanted to answer any questions on homework. Homework is due tonight. And if there were no questions by the end of class, I wanted to begin the next section. So, at this point in time, any questions for the homework time?
21.
21. 21. 21. 21. 33. 33. 21, 33. Come on, 21's bad.
What one?
21's not so bad. What else? Okay. Any other questions? Okay. I'll start on 21 then. 21. We have the following integral. The integral from the natural log of x quantity squared over x dx. Now, for this particular problem, what I'm going to do is I'm going to do u substitution. But I have to be clever with how I choose my u. So there's some decent options here.
Natural log of x, no other option.
Okay, that is the best option. So I'm going to choose my u to be the natural log of x. Why is that specifically the best option there, Michael?
Because there is a 1 over x in the problem.
Because the du is in the problem. Du is equal to 1 over x dx, which is in the problem right there. So, let's write our new function. So, everywhere we see a natural log of x, we replace with a u. So instead of natural log of x squared, we're going to have u squared. The x and the dx are going to be merged now into du, giving us a very simple integral. Now, as a reminder, when it comes to basic integrals, you use the power rule, which is the opposite of power rule for derivatives. We add 1 to the power and divide by the new power. So, we add 1 to the power, u squared becomes u cubed, and divide by the new power. So this becomes 1/3 u cubed, and then because it is an integral that is indefinite, plus c. Finally, in order to find our exact solution, we want to make sure we put our problem back in terms of x. So wherever there's a u, we replace with ln of x. 1/3 natural log of x quantity cubed plus c is our solution. When you get the right u and see how it fits together, it's easy. But getting that right u is the best part. Don't make me direct.
Yeah, 90 to 99 is pretty much the same exact problem. Yeah, it took me 5 tries. It's freaking average value.
Yep.
I didn't pay attention to the instructions, so I went from 97 to the right.
I'm not going to tell you that you should pay attention to your instructions. I'll let the math problems do that for you.
49 or 51 is just telling us to integrate and solve for C.
Yes.
Okay.
So, Reggie asked about 4951. There's 2 parts to it. First, it said sketch 2 approximate solutions. That's, remember we do the follow the wave effect. So we put our dot here, we follow to the left. What is the lines doing? Well, it's indicating we should be going down and then leveling off. And then to the right, it looks like it's leveling off, so it looks something like one solution. Something like that. And the second piece asks us specifically to take this function and integrate it with this specific solution. So finding c using that value. Do not forget the second part. That is why the solutions are attached, so you don't forget. Now it says to graph 2 versions of this solution. So I'll graph one that does not go to that point. Down there. Alright. Let's go now to 33. Answer question. 33 says the integral of cosecant of 2x dx. Oh, come on.
So why don't you just work out the integral back here?
33. Integral cosecant of 2x dx. So in this case, I'm going to do a u substitution. because I cannot integrate cosecant of 2x. I could integrate cosecant of 2u, or sorry, cosecant of u, but not of 2x. So what do? Make my u just 2x. Again, I have an integral of this, but not the way it's currently written. So I get rid of the piece that's currently causing problems. Give me du is equal to 2 dx, or 1/2 du equals dx. And now I make my change. The 1/2 I will move out front. The dx I replace with du. So I have 1/2 du in place of dx. Everywhere I see a 2x, I replace with u, so cosecant u. And now I have the new function. This function I cannot integrate directly using my formula. My formula is actually above for me, so I'm going to scroll up there. I go to the cosecant formula. It says this is equivalent to the 1/2 is still out front because it is not being integrated, so 1/2 out front. The integral is negative natural log absolute value cosecant u plus cotangent u plus c. So the 1/2 stays. The rest is just a direct integration of cosecant of u. And now I finish the problem by making sure that I finish the problem in the same terms I started with, x. So negative 1/2 natural log cosecant of 2x plus cotangent 2x plus c. There is my solution.
Show.
Faux show. I like the U version rather than the X versions because it reminds me that I can always do a U substitution to make it like that form. That's why those cheat sheets are typically with the U versions.
On 47, is it just asking us to find out the values?
47?
Yes.
Yes. So you're given F double prime and given F prime. So basically you have to integrate twice. Once to find the F prime and once to find the F function. Would you like to work through 47?
Yes, please.
Sure. So 47. As a reminder, when we talked about these in the past, the derivative of f of x is f prime of x. So it should stand to reason that the integral of f prime of x is f of x. This is a natural consequence, but the thing is, when we integrate, we always have this plus c. I'm going to use this property to find my solution, but I'm going to do it in a couple steps. Here we go. The first thing I know is I have f double prime, and it says in the problem, determine f. So that means I immediately see I have f double prime, I need to integrate twice. I can't do both integrals at once, I gotta do it one piece at a time. So I'm going to integrate it once to find the f prime, then again to find the f function. Each time I integrate, though, I'm going to end up with a plus c. That is why you notice that each one has a given initial condition. F of 1 equals 1 and f prime of 1 equals 1. I'm going to use that to attempt to fill in the c values as I go. Here we go. We have f double prime of x equals 2 over x squared. First thing I'm going to do is I'm going to rewrite this as 2x to the negative second power. Reason being, if I'm going to integrate this form either. So now, if I want to find f prime, I would integrate the f function. So I would integrate 2x to the negative 2 power. This would tell me f prime. So I integrate. What is the integral of this function?
For directions, teachers, please take 1 moment and check your email. Thank you.
Alright, Ricky, you were correct. Okay. The integral of this function should be negative 2x to the negative first power plus c. This is my f prime function. Again, I use this basic power rule, add 1 to the power, divide by the new power, and I get this function. But we know from the problem itself, it states that in the problem, we know f prime of 1 is 1. So I'm going to use that fact. I know f prime of 1 is 1. So I'm going to take 1, I'm going to plug it into this function, and I want to see if the result equals 1. I'll plug it in. Negative 2 times 1 to the negative first power plus c equals 1. Now, 1 to the negative first power, as a reminder, that just means it flips to the denominator. So it becomes 1 over 1, which is just 1. So I get negative 2 plus c equals 1. I move the 2 over. I end up with the following. C equals 3. Which means my correct solution for f prime, which I'm going to put over here, f prime of x is equal to negative 2x to the negative first power plus 3. Alternatively, we could rewrite this now so it's not in power form, because in the next step it's actually not going to be in this form. So I'm going to rewrite it again. This would be negative 2 over x plus 3. So that form is easier now. Notice how I'm able to switch back and forth with those ease, because both systems work fine. Just one is easier for the first part, the other is easier for the second part. Okay, well, let's now find f. So now I want to integrate this function. But now I want to integrate f prime, because if I integrate f prime, it will tell me the f function. So integrate negative 2 over x plus 3 dx. How do I integrate this function?
So I split up the two integrals.
Good.
And then I took the negative 2 out, and I flexed with 1 over x, so it's negative 2 natural log of x plus 3x.
Fantastic. So he chose to do it by splitting it apart, which is a great way to approach this. As always an option. I shorthand, assuming I remembered to split it apart and get it in this form. And then, of course, don't forget we have a plus c. If you don't like having a plus c here, on a second integral, it's common just to write plus d. Remind yourself that they could be different values. Because we know c was 3. This is not the same c. It's the c from f's function rather than f prime's function. So it's really common to put like d here, or just some other letter. So now I take my next step. My next step says I want to determine this value. F of 1 equals 1. So now I take this function. I do f of 1. So everywhere in the function there is an x, I replace with a 1. So I have negative 2, natural log of 1, plus 3, 1, plus d equals 1. So everywhere there was an x, I replace with a 1, and the function should equal 1, based on the initial conditions. Now I should have simplified. Natural log of 1 times negative 2, 0, plus 3 times 1, plus d equals 1. Subtract. Combine like terms. What do we get for d? Negative 2. So that means my actual solution for f is this function. Now, to reiterate how this function works and how this question is read, what this means is, let's think back to physics. How I think about physics and the relationship between the functions. We were given the acceleration function is this. We know the speed at 1 is 1. We know the position at 1 is 1. That's another way to think about this kind of problem. Or you could think about it not with physics, but with the slope and curvature. You could say, hey, this is the curvature equation. The slope at 1 is 1. The value at 1 is 1. They all mix together to form a function of how it interacts with the environment. What do you think?
You said the acceleration function was f double prime, then you said the position function was f.
Oh my gosh, sorry. So the velocity of 1 would be 1, and the position of 1 would be 1. Thank you for correcting me. I appreciate it. There's different ways to ask the same question. Sometimes you can feel like these are very cold functions, like you don't feel that they fit anywhere in our understanding. They always do. They either fit into the physics form, where it's acceleration, velocity, position, or they fit into the graphing form, where it's location, slope, and curvature. So that was a favorite question. Thank you for asking that one. Sydney, that was great. Any other ones from the homework you want to see? All right, I'll give you a moment while I slowly open the text to the next section. Oh no, the next section might take me a minute to find it.
Why?
I wonder if we'll have a question by then. But no. Yes.
I don't want to have a party. A party and finish my paper.
Inverse functions.
Oh, yay. Finally. What about that?
Okay, any last minute questions? What?
73.
73? I was going to say, didn't we go to 59?
Wait, what are the other ones? 59?
These ones? These are just involving u. So in this one, your u is theta minus sine of theta, and its derivative is 1 minus cosine of theta, so it's actually really nice institution. It's weird. A lot of these have really nice u's.
And didn't we do 995?
Yep.
I thought it was 97.
97.
I just one of those.
And we did the average value questions yesterday. Don't forget the modification is 1 over b minus a in front of the integral.
And then 99 you said just use ln of x as your
Yes.
u.
Just like we did with number 21. Because again, the derivative is 1 over x. We have 1 over x in the problem. Sometimes for questions like 99, what I have to do is remind myself that this is one way to write the problem, but there's another way. I can write this as 1 over x times 2 ln x. I like writing it that way sometimes because it reminds me that the 1 over x is in this problem, and so I can see, oh, natural log, that becomes 1 over x.
I guess we can just start doing it in order.
Is that one the absolute value one too? 99?
99? It does. But because the numbers are bigger than this one, and the absolute value ends up going away. Remember, you're plugging in. That's you times what?
And then you do like the average.
So it's 1 over b minus a? For this function, you do 1 over b minus a times the integral of the function. And the solution for number 99 should be 1 over e minus 1.
I kept getting 1.
If you were silly, you weren't doing absolute value function. Or, sorry, an average value function.
It's because I wrote down the problem. I went to my next class and I forgot it was. I'm always putting whatever.
Okay.
I'll write it down.
Let's at least have some discussion today. We will not start the next section fully. But let's see what you guys remember from algebra. See your slept since then, I hope. Alright. The next section is all about inverses. Inverse functions. First of all, everyone remember what an inverse function is?
What if you replace x with y and you solve for y?
So that's the common way to find it. You are correct.
Is the I'm trying to remember the relationship.
So hold on a second. What you said was it's when you replace x with y and then solve for y again. So it takes a function and normally allows you to back solve for the other variable. This is true. But that gives me a way to find the inverse. It's not really helping me describe what the inverse actually is.
They cancel out to equal 1.
So the idea of an inverse function is they cancel out, not necessarily to equal 1, but to equal the value you put in. So in other words, if you take the inverse with the original function, they should always cancel in some way. So if you were to plug in 3, the inverse and the actual would end up giving you back 3. It would always iterate back itself. That tells me where to use the inverse. But again, that's not really telling me what an inverse actually is.
Vertical and horizontal asymptote.
Now we're reaching a little bit, Ricky. Any other ideas? It's hard to define math terms sometimes because we're used to using them a lot, and I'm used to talking about them.
Reflection of a function over its axis.
Actually, that is correct. That is one way to think about it.
Yes.
Yes, Ricky, that is good. An inverse. There's a few ways to talk about it. It is the reflection of a function across y equals x. That is one way to do it. More of what you were talking about, Michael, was it's the interchanging of variables. More specifically, what you said was you replace y with x and x with y. That is important in understanding what an inverse does. But in terms of the science of it, this swaps the inputs and outputs. Or in the science side of it, the independent and the dependent. So I like talking about realistic equations with this kind of thing. So normally, if I input a time and get out a distance, the inverse will allow me to put in a distance and tell me the time. It's designed to swap the variables around. Swaps the inputs and the outputs. If you're talking about a position function, which normally you plug in t, you get a position. Well, the inverse will allow you to plug in a position and it would tell you how long it took to get there. You talk about temperature functions in physics. We have a reaction happening where after a certain temperature is reached, the reaction forms. Now you can work it backwards and say, hey, if I want the reaction to form this much, I have to get this temperature. It's designed to work backwards of each other. That is the idea of an inverse. Now, the book shows a little interesting picture. I think this picture is neat. If you want to go farther in mathematics, you'll see a picture similar to this a lot. It is called a topography picture. The idea of it is it takes a visual form to how this function is designed to work. So over here, we have the box we're going to call the inputs. Over here, we have a box we're going to call the outputs. Hey, in topology, all things are circles and all things are boxes.
Everything as a whole.
That's right. So, what a normal function does is it takes the input values and creates output values. So that would be our f function. I plug in 3, get out 7. Plug in 5, get out 2. I plug in a number and I get out the y value. I plug in x, I get y, f of x. So, what the inverse function does is the exact opposite effect, where I start by plugging in what should be outputs, and instead it will tell me what inputs get me there. Think of it like Jeopardy. I give you the answer, you tell me the question. But in terms of functions. So I say, hey, the position is 5 miles away, tell me the time it took to get there. As opposed to most functions which do the exact opposite. I give you a time, you tell me where it goes. So again, it's designed to work this thing backwards. Now, graphing-wise, bringing it back together kind of form this statement about how it's a reflection across the line y equals x. That is correct. This is a natural consequence of how this works. Ricky also mentioned that it usually results in a value of 1 when you put them together, but it's not quite perfect. Instead, it creates a value of x. So in other words, the f function and the f prime function of whatever variable you're working with will always end up canceling, leaving you whatever you plug in. So if I plugged in 2, I get out 2. If I plug in 5, I get out 5. They always cancel each other because the inverse has this property. It works the other way as well. If I inverse the original function, I will also get back the input. It has this natural property that it's canceling. And again, don't think of x as the variable now, think of it as your input, whatever you're plugging in. So if I plug something into the original function and then invert it, I'll get back where I started. If I plug something into the inverse and then plug that into the original function, I'll get back where I started. And again, this picture is helpful to see that because if I start here, I end right back there. If I start there, I end up right back where I started. I always end up back where I started. Yes, ma'am? Don't. Good. So?
Is that f prime of x or just like f?
Inverse. So f, the negative first power, represents the inverse function. It is not a power. Thank you. No, you should have. Thank you, Abby. Thank you. They're naturally canceling functions. I guess I should just put a little line in front of it. Pretty nice. Okay. Next thing I should tell you. Not quite an obvious statement, but when you think about it, it'll make some sense eventually. Not every function has an inverse. One more time. Not every function has an inverse. Or at least not a unique inverse, where we only get one solution, one equation every single time. Instead, inverses can often have multiple components, and they could be piecewise, or they could just possibly generate multiple solutions. Trig functions are famous for this because trig is cyclical like that. But there is a collection of functions that always have unique inverses, and are therefore the main focus of a lot of calculus study. These are functions that have two properties. These are functions that are, so an inverse exists if. Now this is a guaranteed exists. Are there functions that will break the rule I'm going to talk to you about and still have an inverse? Yes. But this is a guaranteed one will exist, meaning you can tell you go find it and we're not in my wild goose chase. First, if the function is continuous. So if you want to guarantee one exists, you need to have a continuous function. If you want to guarantee one exists, you must be able to differentiate that function. If you wish to guarantee it exists, you must be able to take a derivative. So it must have a solution. Other things. It must be one-to-one and onto. Now it's been a little while. We talked about these at the very, very, very beginning of the year, so let's remind ourselves. What does one-to-one mean?
Exactly. 1 second. It passes a horizontal and vertical line test, and I'm not sure what that means. Outside of that.
So, one-to-one?
Doesn't cross any of the same points. There we go. I don't know. I know what it is.
If I have one input, there's only one output. If I have one output, there's only one input. So it has to pass the horizontal line test and the vertical line test. The way one-to-one means is every input has a unique output, and every output has a unique input. Yes. Onto is a similar concept, but with a very different premise. It's the idea that there exists an output for every input. every possible input and output exists, meaning there's no gaps in my function. So it doesn't just pass the horizontal and vertical line test, but also passes the horizontal and vertical domain test, meaning there's no gaps in my domain, there's no gaps in my range. If all four of these cases are met, you will guarantee have a workable inverse. One last time. Do other functions have inverses? Yes, they're just not always functions, meaning they won't have these same four properties. Example, the equation y equals x fits all four of these categories. Why does it fit all four categories? Well, there's no holes, there's no asymptotes, so it's continuous. Number two, I can differentiate. If I take the derivative of that function, I get 1, I'm good. Is it 1-to-1? Yes, it passes the vertical and the horizontal line tests. Is it onto? Is every possible input and output found? In other words, is there any gaps in my domain? No. So that guarantees have an inverse. However, y equals x squared is not. Here's why. It does have an inverse, but it's not an inverse function. Here's why. Is it continuous? Yes. It has no asymptotes, it has no holes. Is it differentiable? Yes. We can take a derivative of x squared, it's 2x. Is it 1-to-1? No. Is it onto? No. I cannot possibly get negative y values, therefore there are gaps in my range, therefore it is not 1-to. I cannot possibly pass the vertical line test and the horizontal line test because the horizontal line test I'd have 2 values everywhere there exists a point except 0. X cubed. That passes. There's an inverse. That's a function. Again, x squared has an inverse, but it's not a function. It's something else. It's an equation. Remember, functions are ones that have to have very specifically pass the vertical line test. So it's possible that it breaks that piece, which it does. X cubed works. Other ones that we've seen that work, the log function does not have an inverse function. Wait a minute. It's been a year. I remember something we did last year and had to recall it. On to is in the next section. I remember this from last year. I did the same mistake last year, but I caught it this time. Ah! On to is required for something else. We'll get to that later time. Apologies, I'm so sorry. I did it last year too. I should have clarified this one. I knew there was something I couldn't remember. But I must have thought it wasn't that important. It is. Because there is a function we've seen that does have an inverse. Y equals natural log. The natural log function does have an inverse. In fact, all log functions have an inverse. Did anybody else notice that when we talked about the logarithmic function, we only talked about the natural log? Like there's a bunch of natural log functions. There's a bunch of other log functions. Because there will be derivative rules for those too. It's just the natural log is the easiest to work with across the board. The other functions, they do have derivatives, they have integrals. They're just worse. They require an extra step or two to get them right. So, the natural log function does have an inverse. And that inverse is actually a pretty well-known function too. Anybody know? Do what? You're close. So, the natural log function and e to the x function are inverses. They match our description that we talked about before, where it is reflected across the y equals x axis. It matches the description that replaces values backwards, like it does everything an inverse is supposed to do. In fact, you can blame e to the x for creating the natural log function. Much like how a square root was created to undo the square operation, the logarithmic function was designed to undo the exponential function. They are natural opposites of each other. It's kind of weird that we talk so much about math. And a lot of it is created specifically to undo some other problem. It's actually been the way the whole time. People were adding long before they learned subtraction was a thing. Yet it made sense. Multiplication is easy to see in nature, not so easy to survive. We'll talk more about inverses and their derivatives. Thank you. Don't forget the homework. If it is not finished, please turn it on Google Classroom or send me an email. Thank you, Mike.